Hello everyone. We are continuing class 12 chemistry chapter 9 coordination compounds. Under that we are discussing crystal field theory. Part 4 color of coordination compounds as explained on the basis of crystal field theory. Please watch this video after watching the earlier 3 parts so that you can understand this better. We have already discussed crystal field stabilizing energy. Different ligands have different crystal field stabilizing energy. Please recall spectrochemical series. Before we continue, I am Anandavali from Guidance Education channel. Please watch my channel and support me through your subscriptions, likes, shares and comments. Thank you very much. I welcome you all to this video. The central atom of the coordination complex is a D block element. You already know that. D block elements form colored compounds. Let us see a few examples. Consider these complex ions. Pentamine chlorido cobalt 3 ion. Cobalt is the central atom and it is violet in color. Next one is pentamine aquo cobalt 3. It also has cobalt as the central atom, but its color is red. Example 3. Hexamine cobalt 3. Here also the central atom is cobalt, but the color is totally different, yellow orange. Fourth one, hexacyano cobaltate 3 ion. It is an anion complex as the name suggests. Here also the central atom is cobalt, but the color is totally different from the rest. It is pale yellow in color. Tetra aqua copper 2. In your laboratory you would have seen blue colored copper sulfate which is slightly wet. If it is heated it will become dry but it will lose its color. Anhydrous copper sulfate is white in color. The central atom is copper and the color is blue as suggested earlier. Last example, hexa aqua titanium 3 ion. It has titanium as the central atom and it is purple in color. In the first 4 coordination entities, though cobalt is the central atom, that is the central atom is the same, but their color is different. In all these 6 compounds, we find that the ligands are different. In the first one, chlorine and ammonia. In the second one, ammonia and water. Third one, ammonia alone. Fourth one, cyanide group. Fifth and sixth one has water as ligands. We have to understand why this is so, and that too on the basis of crystal field theory. You have already learned that when the central atom is approached by a ligand, crystal field stabilizing energy comes into play. That is delta O for octahedral complexes. Now we are discussing octahedral complexes. Crystal field stabilizing energy is a form of energy. It is exactly similar to the energy of visible spectrum of light. That is, it has the same order and magnitude of the photons in white light. That is, energy packets in white light. That is, the visible part of the spectrum of light. You have already learned electromagnetic spectrum, the spectroscopic study of light. You have also learned that when white light is passed through a prism, it splits into 7 colors. That is the rainbow colors. The crystal field splitting or stabilizing energy is similar to the energy of these colors. Therefore, even after the crystal field splitting as a result of the approach of the ligand, the central atom can absorb this energy further and get excited more. Due to crystal field splitting, the electrons in the D subshell is already arranged suitably in the T2G or EG energy levels. The electrons in the T2G energy level further absorbs energy from light, which will be greater than the crystal field splitting energy, and get excited further. The excited electrons will then move from T2G to EG energy level. You have already learned hydrogen spectrum, absorption spectrum and emission spectrum. Only the remaining colors will be reflected back. That is, the remaining wavelengths of white light, that is, which are not absorbed, only get transmitted, and all of them get transmitted together and impart a particular color to the compound. The color will depend upon the wavelengths which are transmitted. Different metal ions absorb different colors. So the transmitted or reflected wavelengths also will differ. Energy needed for the transportation of electrons from the T2G to EG level will be different for different ligands, though the central metal atom may be the same. So the same metal ion, that is central metal atom, may reflect different colors in different types of coordination complexes with different ligands. We may say the color that is transmitted by the central metal atom will be complementary to the color that is absorbed. Let us go back to the examples which we considered earlier. Pentamine chlorido cobalt 3 absorbs yellow and appears violet in color. Pentamine aqua cobalt 3 absorbs blue-green color and appears red. Hexamine cobalt 3 ion absorbs blue and appears yellow-orange. You can understand the rest from the table that is given. Okay. I will explain this in detail with the example of hexa-aqua titanium 3, which is purple in color. Titanium is the central metal atom and there are 6 molecules of water as ligands. This ligand approaches titanium. Titanium atomic number 22 and the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2 and 4s2. In this complex, titanium has a charge of 3 plus. So it has lost 3 electrons. 2 electrons in the 4s orbital and 1 electron from the 3d orbital is lost. And the electron configuration of titanium 3 plus ion will be 1s2, 2s2, 2p6, 3s2, 3p6 and 3d1. Atomic number does not change because atomic number is a number of protons. There is no change in protons, only change in electrons. The ligands are linked to the titanium ion and therefore there is crystal field splitting. Let us see the pattern of crystal field splitting and electron distribution. The energy increases from the T2G orbitals to the EG orbital. The single electron in 3D is in the lower energy T2G level. The absorption peak for titanium has been observed as 5000 angstrom, which is equivalent to 240 kilojoules. This is much greater than the crystal field splitting energy. So the ion absorbs the corresponding energy from white light, that is the blue-green region. The rest of the colors are transmitted, that is reflected. So the combination of all these wavelengths which are reflected gives it purple color. If only all the 7 colors are reflected, it can have white color. It is the D1 electron which absorbs energy and it gets excited and moves to the EG orbital. The electron is transmitted from T2G orbital to EG orbital. The complex is purple. So, crystal field theory helps to explain the color of coordination complexes. In the ion complexes which we considered earlier, In the case of the first four complexes, the central atom is the same, the ligands are different. The colors absorbed and transmitted are also different. So we can understand ligands play a very important role in deciding the color of the complex. Here the different ligands are water, ammonia, cyanide group and chlorine. From the spectrochemical series, we can understand that the crystal field splitting or stabilizing energy for chlorine is less than that of water, less than that of ammonia, less than that of cyanide group. Therefore, the energy absorbed by the metal ion in these different compounds will be different. Therefore, the color transmitted also will be different. I hope the video was of great use to you. If you think it is useful, do like the video, share the video with your friends, leave your feedbacks as comments and also subscribe my channel. Thank you very much. We will meet in the next video with another important topic. Till then, bye. Take care.